All right, so here we are in chapter 8. Now, I know my notes say chapter 7, but that's because this is with a different book. So I'm just going to write chapter 8 here, okay? And we're going to be talking about estimating a population proportion. So the key concept here is we are going to learn the methods for using a sample proportion to make an inference about the value of the corresponding population proportion, okay? Now, this section or these guided notes will only focus on P, which is our population proportion. Okay, you got to remember that. Okay, but this will also work with probabilities and percentages. And there are three main concepts that we're going to be taught here. First, point estimation. Second, confidence interval. And then third, determining sample sizes. Okay, so what we're going to do is we're going to be constructing confidence intervals of a population proportion. We're going to identify the necessary requirements for the procedure, and then also determine whether or not we can do it. And then lastly, we're going to develop the ability to determine the sample size necessary to estimate a population proportion. So let's start off with just some basic definitions, okay? So if we want to estimate a population proportion with a single value, that is the point estimate that we are talking about. The best estimate is going to be the sample proportion, which is p hat. So a point estimate is a single value used to estimate a population parameter. Now, we have things called biased estimators, but then we also have things called unbiased estimators. All right. So I'm going to go ahead and I want to just define what that is. So an unbiased estimator is when we use p hat as the best point estimate. And remember, that's a single numerical value of p. We use this because it is unbiased. And it is most consistent of the estimators involved. Okay, and the reason that we say, excuse me, that is unbiased, because our standard deviation for p, or for p hat, I'm sorry, tends to be smaller than the population variance for the population proportion, okay? So here's what's happening, all right? When we think about a point estimate, all right, what we're really asking here is, what is going to be the best statistic that we can use to try to estimate this population parameter? So I was once taught, and in your book says this, but I was taught about this in chemistry a long time ago, all right? And within chemistry, we were always concerned with basically precision and accuracy, okay? Now, let me show you the differences here, all right? Here's a target, and here's our bullseye right in the middle. All right, there's our bullseye, okay? And somebody who is very precise, okay, but not accurate, would look like this. All right? So notice that all the X's represent where this person shot. That's where they hit the target, okay? And it's very precise because all their shots are around the same area. However, they're not accurate at all because accuracy is the bullseye. All right? Now the second example here. All right? Here is somebody who is very accurate but not precise. So, give me a second here. I'm going to shade in my bullseye real quick. All right. So notice here, this person hit the bullseye like 3 times, but they're still kind of all over the place. So I would say this person is accurate, but not precise. The last example demonstrates both precision and accuracy. And obviously, I think you can guess. All the X's will be near the bullseye, and they're all close together. All right? So when we think about unbiased estimators, what's happening here, I don't know where my X's went. They disappeared on me. What's happening here is our sample deviation, our sample variance is very small when you compare it to the population variance. In other words, you're getting this situation right here. You're getting the nice precision and accuracy that we're talking about. Now, in the world of chemistry, when you're doing analytical chemistry, all right, mixing things together and producing new compounds and stuff like that, you do kind of like, it's called stoichiometry, which is just figuring out, okay, you have X grams of this, X grams of that, how many grams of your product you're going to produce, and we call that a theoretical yield. All right, theoretically, you should get this much, but in actuality, you don't, because, well, people are messy, and sometimes we don't get all the little droplets out of the flask and everything like that. So you get an actual yield, which is always less than a theoretical yield, but you want to be as close as possible. Okay? So the question becomes, all right, well, if our goal is to estimate our population proportion P using P hat, how do we calculate P hat? And what's nice is you already learned how to do this. So P hat is going to equal the number of successes over the total sample. All right? Now, we learned that back in Chapter 7, okay? So what I'm going to do here is I'm going to write out a little example. It's going to be really simple, and we'll calculate P hat. It'll take us 2 seconds, to be honest with you. So let me write out the example first. All right, so I am back, and here's our example. So in a study of cell phone use and brain hemispheric dominance, an internet survey was emailed to 2,564 patients selected at random. 1,027 surveys were returned. All we want to do is just find the best point estimate of the population parameter P. All right, now remember, we are estimating P. We have no idea what P is. However, our best point estimate for this is going to be P hat. And we just learned is that P hat is going to be the number of successes, in this case, the number of surveys returned, 1,027, over the total sample space, in this case, 2,564. And when you do the math on that, you get 0.401. So right now, our best point estimate is 0.401, or approximately 40% of the population. Okay? Now, I have no idea what was on this survey. I don't know the relationship between cell phone uses and brain hemispheric dominance. All I know is P hat is going to be our best point estimate to try to estimate this population parameter. So that leads us into our next question, which is, well, why do we need confidence intervals? Because remember, we're trying to estimate what P is. All right? So why do we need confidence intervals? We found that P hat equals 0.401. Okay? That's what we found. But the question becomes, how good is it? Okay, how good of an estimate is this? All right. So what confidence intervals allow us to do, confidence intervals will give us a much better sense of how good an estimate really is. All right? Because here's the thing. All right? Let's think of it this way. Let's say you were concerned with cell phone usage and brain hemispheric dominance. I have no idea why you'd be interested, but let's say you were interested in this, okay? And let's say that cell phone usage had like a negative effect. All right? And that's really important because I don't know about you, but I am addicted to my cell phone. And I know you all know what I'm talking about. All right? When you're standing in line at Target or Walmart or Shop and Save or Giant Eagle, you're standing there. First thing you do, you grab your phone. You start looking at things. Then you put your phone back in your pocket. Now, I know all of us have experienced what I'm about to tell you. I call them phantom vibrations, where you think your phone vibrated, but it didn't. But you go in your pocket, you pull your phone out, and you check it. Then you're like, oh, nothing happened, so you put it back in your pocket. And then 15 seconds later, you think it went off again, so you pulled your phone out again and you looked at it. Like, it happens to me all the time, all right? Now, this estimate of 0.401 or 40% of the population experience this this negative effect, okay? The question is that 40% really good? I mean, wouldn't it be, think about it this. What sounds better? 40% or 35% all the way up to 43%. All right? This allows room for error, okay? It allows room for error, and that's going to be huge when we start talking about standard error and margin of error coming up, all right? This p-hat, which is 0.401, what you're telling me is this is exactly what it is. And if you don't nail that every single time, then I'm going to sit there and go, I don't think this person knows what they're talking about, because they're always wrong. However, if you give me a range of numbers, that allows some leniency. It's kind of like when you go to the store and you buy a 20 ounce of Coke. I love Coca-Cola. It's my favorite drink, especially if it's like ice cold, all right? Do you think every single can of Coke or every single bottle of Coke has exactly 20 fluid ounces? Or do you think there's like a range of numbers it can be? And as long as it's within those range of numbers, I can't really sue Coke. So think about that. There was a huge court case about this one guy who sued Subway because over the course of like a year and a half, he would document the length of every single sub that he bought because they advertise a foot long and he wasn't getting a foot long. So he sued and won. So you got to be careful with this. All right. So what exactly is a confidence interval? Okay. Why do I have it? Okay, sorry. I got a little confused there for a second. I was reading what is a confidence interval and then what is a confidence level. So let me go ahead and try this over again. So a confidence interval is a range of numbers. We'll say range of values used to estimate the true value of a population parameter. Now, sometimes we denote it as just CI for the confidence interval, okay? But we do got to be careful about creating a confidence interval because, like I said early up above, where you see the 35% to 43%, all right? I want to be confident, but it allows me some error that I was just talking about, and we call that a confidence level, okay? So what is a confidence level? Well, the confidence level is the probability. Now we abbreviate this as 1. I can't write it. Come on. There we go. 1 minus alpha. So that little Greek letter is called alpha. All right. So the confidence level is the probability that 1 minus alpha actually contains the population parameter. Assuming that the estimation process, in other words, how you collected your data and your method and all that stuff, is repeated a large number of times. Remember back in chapter 7, we were talking about central limit theorem and how when you get really large sample sizes, no matter what your distribution is initially, if you keep doing the experiment over and over again, you will start to approach a normal distribution. You will find that middle value. Well, that's exactly what this confidence level is going to help us to achieve, okay? But, and this is the big but, there's always going to be some room for error. So, what are the most common confidence levels? Well, the first one's going to be 90% or 0.9, and the corresponding value of alpha is going to be 0.10. All right? Then the second most important, actually, to be honest with you, I would argue this is the most important, is 95% or 0.95. Alpha is going to be 0.05. And then the last one is 99% or 0.99, where alpha is going to be 0.01. All right? So here's what we're saying here. I'm just kind of zooming out here because I want to highlight something real fast so we can talk about it. All right. So earlier I said, okay, what if we created this confidence interval of 35% to 43%? The first question I would ask you if you came to me, if you approached me about this, I would say, well, how confident are you? Now, if you told me you were 95% confident, I would go, oh, that's pretty good. But now we have to understand what that actually represents, okay? So the key is this estimation process is repeated a large number of times, okay? Now, what you do not want to say is that there's a 95% chance that the population parameter is contained, all right? Now, let me write that down, and I'm going to put a big X through it. I'm going to write it in red because that is wrong. We do not say there is a 95, or another way you could say it is 1 minus 0.05 confidence interval that the true parameter is between 38% and I think I used 43. Was it 43? Yeah. It's 35 and 43, my bad. 35% and 43%, all right? We do not say that, okay? That is incorrect. What we are saying here is if we were to repeat the process. So here's what this is saying here. Now I'm going to write this in green because this is good. Green is good. What we are really saying here is if we repeated, and I'm going to use some static numbers here because they're really easy to understand. If we repeated the process, let me be more specific, the estimation process 100 times. 95 of those times, P would be in between 35% and 43%. That's what we were really saying here. And that's what this picture underneath on the next page actually represents. Okay? So if we have a 95% confidence level, what that tells us is that the process that we are using in the long run will result in confidence intervals that contain the true population proportion 95% of the time. Okay? So if I'm going to zoom in here real quick. So here are my upper and lower limits of this confidence interval, which I didn't even show you how to calculate yet. I will, though. The true population parameter, P, is 0.5, but what the 95% confidence interval tells us is that, now you can count, I think there are 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Good. So now I'm going to erase all of them. So what the confidence interval tells us is that if we were to repeat this process 20 times, only one time, which is highlighted in green right here, only one time will our interval not contain P. The other 19 times, it will. And that's what this is showing us here. So notice each one of these, and I need to kind of just shrink down my marker here, and I'm going to pick on this one. Those little dots on the end of that line segment represent the upper and lower limit for that specific experiment. And what happened was somebody repeated this experiment 20 times. One time did they get an interval that didn't contain P, which they were trying to estimate. Now, we're telling you it's 0.5 here. Oops, sorry. We're telling you it's 0.5, but if you didn't know, you could go to your supervisor or your research committee and say, hey, I'm 95% confident that the technique I used over and over again, I'm 95% confident that the true population parameter is in between these two numbers. All right? That is really good stuff. Because, once again, you're allowing us a little bit of room for error. All right? But you're telling us that you're 95% confident that you're capturing that population parameter. All right? Boy, this, like I said, this is like my favorite part of the class because we're taking everything that we learned and we're applying it to like real life situations. So what I want to do now, all right, is I'm going to write, how do we interpret this? All right, so to interpret. And this is going to be massive. All right? Because you're going to do this every single time. All right? You always start off with, well, not always, but somewhere along the lines like this, because I know I was looking at your homework and they kind of word it differently, but it's the same. It means the same thing. We are 95% confident that the interval, boy, it'd be great if I can write the word that. So we are 95% confident that the interval from, and I'm going to use our data values from that example that I made up. So our interval from 0.35 to 0.43 actually contains the true value of the population proportion, P. Now, if you're doing mu, it's this. You set it up the same way. It's just you say the true value of the population mean, mu. You just change the last two words, or you change the last word and I guess the last symbol. But it's basically the same thing. Okay. So now we're going to get into the nitty gritty of this. Now what we're going to start talking about is, okay, what does this look like on a graph? What are critical values? How do we actually calculate a confidence interval? Because like I said, I haven't showed you this yet. All right. So before I go through all this stuff, I want to just draw a picture here, and I'm going to show you what this means. All right. So here we have a normal curve. All right. And we know that right down the middle is our true value. We have no idea what this is, but we know it's going to be right down the middle, okay? Now, in order for us to create a confidence interval, we need a margin of error, okay? So we need our margin of error. Now, the margin of error, all right, so I'm just going to call it ME, is going to equal some critical value. You know what? Let me write it underneath. I think I'm doing a bad job. Here we go. So the margin of error, we'll say ME is going to equal some sort of critical value multiplied by the standard error. So what does all this stuff mean? Well, let me show you, okay? The true value is right down the middle, okay? We're going to have our lower limit, and then we're going to have our upper limit, okay? This distance from our true value to the lower limit or the true value to the upper limit is going to be our margin of error. And there's two of them. There's a minus the margin of error, and then there's going to be a plus the margin of error, okay? So if we were concerned with a 95% confidence interval, okay, then what we would say is the standard error is negative 1.96 to the right and positive 1.96, or I'm sorry, negative 1.96 to the left, positive 1.96 to the right, times the standard error, okay? Now, if you're asking yourself, whoa, what in the world is this 1.96 stuff, okay? This is what we call our critical value, okay? And let me write it off to the right here. Our critical value is going to be equal to alpha over 2. Now, let me explain what this stuff means first, okay? I'm going to come back over to here, and we're going to talk about critical values. Then we're going to fill in this chart, and then I hope it all starts to make a little bit of sense. So a critical value is a number. So critical value is a number on the borderline. Sounds like a 1980s song. On the borderline separating sample statistics that are significantly low or significantly high, okay? And here's the first time you're going to see this. The Z alpha over 2 number is a critical value that is a z-score. So this is a z-score. And remember, z-scores are a measure away from the mean. They can be to the left or to the right. But this is a z-score with the property that it is Come on, you gonna let me erase? That it is a border that separates an area of alpha over 2 in the right or left tail or tails of a normal distribution. All right, so big definition. Let me tell you what it does. All right. Underneath here, we'll worry about that table in a second. We know the true population parameter P is going to be right down the middle. All right. Like I said, we also know we have an upper and a lower limit, but let's say we want a 95% confidence level. All right. What I want to know is, since this is 95% confidence level, and we know that the total area under the curve is equal to 1, what I want to do is I want to find this distance on the left and right hand sides of this population parameter that I'm trying to estimate. I want to know what is that distance so that I can separate this area right here and this area right here. Now, there are two areas that I need to be concerned with, a lower area and an upper area. That's why we use alpha over 2. In other words, this alpha is going to get rid of the area that I don't want. I want 95% of all my possible population parameters to fall in between these two numbers, which we call the lower limit and the upper limit. So this is our negative z alpha over 2 value, and this is going to be our positive z alpha over 2 value. And it's because, remember, the true population proportion of a standard normal distribution is 0. Then to the left is going to be negative values. To the right are going to be positive values. So now we can go ahead and start filling out our table above, which are just common confidence levels. So the first one is going to be 90%. And that should look really familiar because didn't we do that up above? So 90% confidence level, which means alpha equals, let me write it out here, 1 minus 0.90, which is 0.10. And then our critical value for that, our z alpha over 2. Now, I'll write it off to the right-hand side. This is going to be z of 0.1 divided by 2, which is 0.05. Okay? Excuse me. So that is going to be 1.645. Now, I know you're probably sitting there asking yourself, where in the world are you getting this 1.645 from? Remember, let me get out my little highlighter here. That distance that we're trying to find to the left and to the right, this margin of error that we're looking for, is a z-score times the standard error. Okay? Since it's a z-score, I can actually look this up. So let me show you where I'm getting this 1.645 from. So I need to go back in time to, I think it's this one, chapter 7. Or is it chapter 6? I can't remember. It's chapter 6. So here we are again at our z-score table. Boy, you thought you were done with this? Forget it. Now, we're interested in a z alpha over 2 of 0.05. Because remember, we want a 90% confidence interval. And we know alpha is going to equal 0.10, or 1 minus 0.9, 0.9 is 0.1, and then divide that number by 2. That's how we got the 0.05. Now watch this. If I take this 0.05, which is my area, remember, let me go back. I hate going back, but I'm going to have to. Remember, this right here is 0.05 area on the left, and this right here is 0.05 area to the right. The total area is going to be 0.10, but if we can find this one, watch what happens. I'm going to go into the body of the table, and I'm going to try to find, now you got to be careful. You're looking for 0.05. Now, luckily for us, there's that little asterisk. So I'm going to zoom in. Do we see the little asterisk right there? Look at the numbers to the left and to the right. To the left, it's 0.0505. To the right, it's 0.0495. So what I'm going to do is I'm just going to follow this little arrow down. So let's just follow it down. And then to the right, and it says area of 0.05 is negative 1.645. Okay? So if you think about this, that is on the left-hand side, and z-scores are always taken from left to right. So if we go over, or base, we even have to do that, due to symmetry, all right, due to symmetry, the other side is going to be 0.1645. All right, now if you wanted to, like I said, you can come over here to the positive. Here it is right here. Follow this all the way down to the left. And it says the z-score of area 0.95 is going to be 1.645. So technically, when I go back into my table, I can put plus or minus 1.645. Now, before I do that, I just want you to kind of look. This is going to be on the positive z-score table. Look down here. It already gives you everything you need. So common critical values for confidence intervals or confidence levels. 0.9, critical value is 1.645. 0.95 is 1.96. And 0.99 is 2.575. So that is exactly what I'm going to put in my table here. 95%. It's going to be 1 minus 0.95, which equals 0.05. Our z alpha over 2 number is going to be plus or minus 1.96. And then 99%, well, that's going to be 1 minus 0.99, which is 0.01. And when you look that up, that's going to be plus or minus 2.575. Now, remember, what we're trying to do is, I think this may be a better way to explain it. Think about a pond. Inside a pond of water, you got all these different fish. No, let's be more specific. You got one type of fish. It's a bass. All right? If you took a fishing line, you threw it in there, all right? You caught the fish, you reeled it in, and you weighed it. Does that weight that you just found of that fish, is that a good representation of all the fish? The answer is no. It's not. It just isn't. It's one fish. You have no idea how many fish are in that pond. You only caught one. But what if you created a net? And instead of catching one fish, you caught 100 fish. And you found the average weight of all 100 fish. Ask yourself the question, is that a better estimate? And the answer to that is absolutely it is. Okay? Because you're catching more fish. You're getting more data about this population. Now, if you have a bigger net, you're going to catch even more fish. And you're going to get a better answer. Okay? The problem is, we don't know what the true proportion is. We can only be confident that it's in between these two numbers. Okay? And that's what confidence intervals allow us to do. All right, I realize this is a lot, but trust me, once you see how this works in action, it's really simple, okay? So the next thing I want to go over is this margin of error thing, okay? Now, within the margin of error, we have the sample error, okay? Now, the margin of error we define, I don't know why I just wrote that. Margin of error we defined as ME equals our critical value, which is going to be Z over 2, times our standard error. Now, the definition of this is when data from a simple random sample are used to estimate so when data from a simple random sample are used to estimate a population proportion, okay, we're going to call it P, the difference between our sample proportion and the population parameter P is considered to be an error. In other words, we know there's going to be there will be a distance between them, and that is error. Okay, and that's okay. Like I said, I'd rather have some leniency in my observations versus catching only one fish and saying, here we go, this is what it is, and then somebody else catches another fish and they're like, well, why is my fish different? Okay, so there's going to be an error there. Now, the maximum likely error is the margin of error. All right, so that's going to be the max. Okay? Now, there is a probability of 1 minus alpha that the difference between P hat and P is our error or less. Okay? So what would be our standard error or less. Sorry, I forgot the S there. So our standard error for proportion is going to be equal to the square root of P hat Q hat over N. All right, now, enough with all these definitions and all this theory stuff. Let's construct some confidence intervals. Let's see how we do this, okay? So let me get on my black marker again. As I said, it's not as bad as what you think. It's just that it's a lot of theory, and I get that. But if you go back to, like I said, the example of the fish, okay? If you catch one fish and you pull it out, you need to ask yourself, is that a good representation? If it's not, you got to find a better way. That better way is called a confidence interval. So you create this confidence interval, and then you tell me, okay, I'm 95% confident that if you were to do this 100 times, 95 times we would capture this true proportion parameter. 5 times we wouldn't. All right? So here's the objective. We want to construct a confidence interval, and we're going to use it to estimate a population proportion. I can tell you this right now. This is very simple to do. And when I go ahead and teach you how to do this for a population mean, it's going to take me like 5 minutes to show you. All the theory was front loaded into this section of notes. Okay? So first, notation. P is going to be our population mean. It's a parameter. P hat is going to be our sample mean. And remember, that is a statistic. All right. N, it's going to be the number of samples. SE is going to be our standard error. ME is the margin of error. All right, so just to differentiate between the two, standard error is equal to the square root of p hat q hat all over n. The margin of error also includes that critical value that we call z alpha over 2 times the standard error, okay? Now, there are requirements. You just can't do this whenever you feel like it. The first requirement, the sample is a simple random sample. Okay? 2, the conditions for the binomial distribution are satisfied. Now remember, that is n times p is greater than 5 and n times q is greater than 5. Okay? Or 3, very large sample sizes with at least 5 successes and 5 failures. Okay? So I'm going to be honest with you here. Every single problem we're going to do is going to meet these requirements because I want you to do this. I don't want you to look at a problem and go, oh, it doesn't meet it. I can just go on to the next one. All right? So how do we actually construct our confidence interval? Well, all intervals are constructed the same way. All right? It's going to be whatever your population parameter is plus or minus your margin of error. So for us, when we're talking about estimating the population proportion, it's going to be P plus or minus our margin of error. So it'll be P hat minus our margin of error, which is less than P, which is going to be less than P hat plus our margin of error. So hopefully now you can see where that plus or minus 1.645, plus or minus 1.96, and plus or minus 2.575 comes into play. Okay? Now, the way that we write this, we can write it like what we have here, all right, which is an interval. Another way is just using parentheses, which you would have learned how to do that if you took like Math 90 or Math 108, all right, and you did confidence interval, or not, sorry, I'm sorry. If you just did interval notation, okay? Oh, sorry, I'm getting lazy here. I need to put ME. All right. And the round off rule, just round to three digits. All right, that's always pretty good. But wait until the end to round. All right? Don't round early. Keep all the numbers that you need. Okay? So, let me zoom out here. So here's the objective. Now, the procedure. Okay? It's really, really simple. Our procedure. Step 1, you always want to verify requirements. Like I said, every single problem I give you, you're going to be able to do it. Step 2, you want to find your critical values, Z alpha over 2. Okay? Step 3, find your margin of error. And remember, that equals Z alpha over 2 times your standard error. Now, this is general. All right? This applies to everything, but, for this, we're going to just do it. For proportions, we're going to do it here. Step 4, find the upper and lower limits. And then step 5, round and then write your interval. Okay? So what I'm going to do is I'm going to go ahead and do some examples of this first, okay? I know we got some other things we got to do in this lecture. This is a big lecture, all right? But it's because it's a lot of theory up front. Everything else from here on out is really easy, okay? But let's go ahead and let's do a couple examples. Okay, I'm back, and here is our problem, all right? So an important issue facing Americans is a large number of medical malpractice lawsuits and the expenses that they generate. In a study of 1,228 randomly selected medical malpractice lawsuits, it is found that 856 of them were later dropped or dismissed. So what we want to do is construct a 99% confidence interval estimate of the proportion of medical malpractice lawsuits that are dropped or dismissed. And then we want to answer the question, does it appear that the majority of such suits are dropped or dismissed? All right. So I'm telling you right now, we meet all the conditions to actually calculate the confidence interval here. So step 1 is done. All right. Now, if we go back and we look at step 2 is we need to find our critical values. So step 1, done. Step 2. Okay, so we need to find, like I said, these critical values. So we want a 99% confidence interval, which means our 1 minus alpha, 1 minus alpha, or in this case, 1 minus 0.99 confidence interval is going to be 0.01. Now, what that's telling us here is this. When we create our normal distribution curve, we know P is going to be somewhere in the middle, okay? I want the total area in both those tails to total to 0.01. So I need the Z of 0.01 divided by 2, which we know that turns out to be, if we were to just calculate it first, 0.005, or, remember from our table, this will be 2.575 plus or minus. So, excuse me, so if you're asking where am I getting this data from, or these numbers from, let me go back, I'll show you. It's going to find all that stuff. Oh, sorry. Section 2, my bad. Here's that table right there. So 0.99 confidence interval, alpha is 0.01. If you were to divide that by 2, you get 0.005, which corresponds to a critical value of 2.575. So if you needed to, that 0.005 number I was talking about, if you go into your body of the table and look at this asterisk right there, that's 0.005. And if you were to follow this all the way down and to the left, here's where it is, 0.005. And notice the z-score is negative 2.575. So, and once you do this enough, you'll start to memorize all this stuff. So our critical value is going to be positive or negative 2.575. Okay? Now, the third step. We're going to find that margin of error. So we know the margin of error is going to be that critical value that we just found multiplied by our standard error. So the standard error is equal to the square root of P hat Q hat over N. Now, this formula only pertains to proportion problems. Okay? Only pertains to proportion problems. Now, I'll go over how do we know if we have a proportion problem or like a mean problem later. So what I'm going to do is I need to find P hat. So P hat comes directly from the problem. We found that in a study of 1,228 randomly selected medical malpractice lawsuits, 856 of them were dropped. So p hat is going to equal 856 over 1228. So if you give me a second here, I'm going to get out my calculator. I'm going to type in 856 divided by 1228 equals 0.697068. Now, do not round this to 0.7. Keep a bunch of decimal places. Only round at the very end. Okay? So this is what p hat equals. Q hat is going to be 1 minus p hat, or 1 minus 0.697068. So give me a second. 1 minus 0.697068 is going to equal 0.302932. So my standard error is going to equal the square root of 0.697068 multiplied by 0.302932, all divided by 1,228. So now what you need to do is you need to take out your calculator and go ahead and find this. And just be careful, okay? If you need to, excuse me, if you need to, do one thing at a time, all right? Just be careful when you're calculating. But I'm going to go ahead and do this all in one step. In fact, no, I'll just do it on my calculator that I have right now. So give me 1 second. All right, so I found my standard error to be 0.0131133. All right? So finally, our margin of error is going to be 2.575 times 0.0131133. Now remember, technically there's a plus or a minus out front. So if you want to leave that plus or minus out front, that's fine with me, okay? But just know all you need to do is just multiply these two numbers together. So 2.575 times 0.01311133 gives me 0.0333767. So I'll round it like whatever that is, 6 decimal places. All right. Step 3 is done. Step 4. Now we find our upper and lower limits, all right? So I can just summarize that by just saying find the interval. Here's what we know. We know the interval is going to look like this. P is going to be directly in the middle. And then you're going to have p hat minus your margin of error. And then p hat plus your margin of error. All right? Now, we found p hat to be 0.697068. And we're going to subtract our margin of error from that. And then we're going to do the same exact thing, except we're going to add the margin of error to that. All right? And what we've basically done here, okay, by doing that, and I'm going to scroll all the way back up, is we found that distance from left to right, and we also found what value do those numbers actually represent that separate the error that we don't want from the area that we do want. So if you just give me a second here, I just type in my calculator. 0.690, all that stuff, minus my margin of error. So I get, and I'm going to round to 3. Now I round to 3 decimal places. So I get 0.663, which is less than the true proportion. And then I do the same thing, except I add it this time. and the upper limit is going to be 0.731. And that is my confidence interval. Now, if you're thinking about this in terms of percentages, 66.3% and 73.1%. Okay? So what we've just done is found our confidence interval. Okay? But now let's go back and let's read the question one more time. All right? They wanted us to find the 99% confidence interval estimate of the proportion of medical malpractice lawsuits that are dropped or dismissed. So let's interpret this first. We are 99% confident that the true population, in this case, it's going to be proportion, is in between 0.663 and 0.731. Okay, that's all this is saying. But now, let's answer the second part of the question. So I'll scroll up. And the second part of the question says, or ask, does it appear that the majority of such suits are dropped or dismissed? Okay, so let's think about that. And we need to go back and we need to look at our interval that we've created. So when we look at our confidence interval and we compare that to the data that we've collected. So p hat is equal to let's just say let's round it to 0.697. That's what p hat was. That is the data we've collected. And when you look at that, notice that that definitely is in between 0.66 and 0.73. Okay, now because this is in between, we conclude that, and think about it. Maybe pause the video, okay? Come back, okay, so in between, therefore, we can conclude that, I already forgot the question. Silly me. The majority of such suits are not dropped or dismissed. All right? So, let's think about this. If our sample statistic turned out to be outside of these numbers right here, then I would say, wait a minute, it's outside of the confidence interval. That is statistically significant. That shouldn't happen because we were 99% confident that the true number of dismissed cases is going to be in between these two, and our sample data is outside of that. But because this is in between, then we can conclude that the majority of the cases are definitely not dropped. All right? They definitely take this stuff very seriously, which is exactly what you want. Okay? So, So I hope that makes sense in terms of just calculating the confidence interval. Like I said, it's very simple, but boy, is there a lot of information that we actually went through here. I mean, tons of information, okay? So let's go ahead and let's do another one here. Okay, so here's our next example. Very straightforward, nothing too crazy, all right? Just random numbers. A random sample of 500 observations from a binomial population produced X equals 330 successes. First, let's find the best point estimate. And then second, let's find a 95% confidence interval that actually estimates the true population proportion here. So, step one, conditions. Well, it's a binomial population. We definitely meet all the criteria. We have over 330 successes, okay? Which means we definitely have a lot of failures, so it's over 5. And n times p and n times q is definitely going to be over 5. So, conditions met. Like I said, I'm not going to give you one that you can't do. 2. Okay, let's find this. Let's find the best point estimate here. So p hat is going to equal the number of successes over the observations. So it's going to be 330 over 500, which when you go ahead and you calculate that, 330 over 500 is going to be 0.66, which means q hat is going to be 1 minus 0.66. So 1 minus 0.66 is going to be 0.34. Okay, let's also find the critical values. So we want a 95% confidence interval. So our z alpha over 2 will equal plus or minus 1.96. Just go to the table and find which one you need. Okay? Step 3. We got a lot of information. We can find our margin of error now. All right? So the margin of error is going to be plus or minus 1.96 times the square root of p hat, 0.66, times q hat, 0.34, all divided by n, which is equal to 500. So if you just give me a second here, I'm going to go ahead and calculate this for us. All right, so I came up with 0.0415. We'll say 22. Just remember, keep more decimal places than what you need. Okay? Step 4, let's find the actual confidence interval now. So remember, this is going to be p hat minus our margin of error, which is less than our population parameter, which is less than p hat plus our margin of error. So 0.66 minus 0.041522. So remember, that's going to be our lower, which is less than our population parameter. And this will be less than the upper limit, which is 0.66 plus 0.041522. So remember, that's our upper. So when I go ahead and just subtract these numbers, I get 0. And I'm going to round to 3 decimal places here. 0.618 is less than p. And now I'm going to add the numbers together to give me 0.70, and I'm going to round to 3 decimal places. So it's going to be 0.702. So here's my interval. Another way you can write this is using interval notation. 0.618, comma, 0.702. And like I said, we always want to interpret. We are 95% confident that the true population proportion is contained in the interval 0.618 and 0.702. So I kind of wrote this one a little bit different, but it's the same exact idea. All right, very straightforward, not too difficult. Like I said, it's all about just following the procedure. Okay? All right, now, luckily for us, we have salt. We can go ahead and we can use salt if we wanted to help us with our calculations. And to be honest with you, I don't know why you wouldn't use it. So let's go ahead, let's open up salt, and I'll show you how to do it with this specific problem right here. So I think we got to go to Blackboard, sign in. Let me pick my stats course. Whoa, what does it look like this for? All right, well, I don't care. Where's stats? Here we go, right here. All right, come down to salt. All right, so here's salt. Now, we are doing inferential statistics here. So you want to go over to the inferential statistics part. And on the left-hand side here in the settings, you're going to see a bunch of stuff, all right? First thing I want you to do is click on confidence interval for mu. Now, I know it says mu, but we're going to change that, all right? So procedure selection, we are doing a one sample proportion. So click on one sample proportion. And then here, it's going to ask you for the number of successes. So for our problem, it was 330. And then the number of trials. Well, we had 500 trials. Now, you just want to make sure your confidence interval is appropriate. We wanted a 95%, so we have a 95%. And then we're just going to click on Generate Results. So click on Generate Results, and I'm going to zoom in here so we can see it. And it literally took us longer to get here than it did to actually type in the information. But as you can see here, we have a 95% confidence interval for P, which is our population proportion. Our lower limit is 0.618, which is exactly what we calculated. The upper limit is 0.701, but if you round it to 3 decimal places, you get 0.702. And then it just gives you some descriptive statistics. N is 500, number of successes was 330, P hat was 0.66, and the standard error is going to be 0.021185. So if I wanted to, oops, sorry. I'm going to go ahead and just take these results and put them into our notes in our video whenever it pops up here. There we go. All right, let's shrink it down a little bit. There we go. Because all I want to do is just kind of draw arrows to everything. There's my lower limit. Here's my upper limit. P hat was the same. All right, we calculated that to be true. And remember, standard error is nothing more than just the square root of P hat times Q hat over 500. And that is going to equal 0.021185. The margin of error is when you kick in that z-score. Okay, that's when the margin of error kicks in. And we found that to be, I forget already, 0.041522. Okay, so there's a difference between standard error and margin of error, all right? But as you can see, using SALT, it was very, very fast. I mean, you literally just had to go in and just type in the numbers. All right, for the previous problem, all right, we had the number of successes was 856. Our total sample size is 1,228. And then our confidence level for that problem was 99%. So when I click on Generate Results, round to 3 decimal places, 0.663 and 0.731. And if we go back to that previous problem, 0.663, check. 0.731, check. All right? So that's how we find confidence intervals for proportions. All right? So this video is already over an hour. So what I'm going to do is I'm going to stop the recording, and then I'm just going to make another video specifically designed or specifically made for doing confidence intervals for a population mean. And inside that video, I'm going to tell you how do you know what type of problem you have. All right? So I'm going to see you in the next video.